A mathematical average can be deceiving. Two entirely different physical realities can sit on a scale and balance perfectly, despite one being a stable solid and the other a chaotic cloud of particles. This scatter plot shows how that happens. We see an upward trend, but individual points are scattered at varying distances. If we only measure the center, the mean or median, we define the fulcrum while ignoring the actual distribution of its mass. To understand the whole story, we need to calculate variability, the spread, scatter, or dispersion of the data points. Accurately modeling reality requires us to mathematically define how values differ from one another, rather than just identifying where they cluster. Analysts typically use two primary frameworks to quantify this spread: the mean-based approach and the median-based approach. Utilizing both is the only way to ensure an analyst isn't being manipulated by an isolated top-line average. The mean-based approach aims to find the average distance of every single data point from the central mean. This is the formal mathematical architecture for population variance and standard deviation. It relies on the summation of deviations, represented here by the sigma symbol. We can test these equations using the 6 possible outcomes of rolling a standard die. A die roll has a mean of 3.5. By mapping the distance from that center to each possible outcome, we find the individual deviations. However, because the positive and negative deviations mirror each other exactly, their raw sum is always 0. To bypass this zero-sum trap, we square every deviation. This forces all negative values to become positive, preventing them from offsetting the results. We then take the average of these squared deviations to find the variance, denoted as s squared. In our die roll example, the sum of these squared deviations totals 17.5. We divide that sum by n-1, a step called Bessel's correction, used to provide an unbiased estimate for samples. This gives us a final variance of 3.5. But variance has a practical flaw. Because the units are squared, a weight measurement would be expressed in squared kilograms, making it impossible to compare directly to our original data. We resolve this by taking the square root of the variance to produce the standard deviation. For our die roll, that square root is approximately 1.87, returning our spread metric to the original units. While standard deviation is mathematically precise, it is highly sensitive to extreme outliers because every single data point influences the final calculation. Consider this dataset of 20 observations, ordered from 1200 up to 7700. If we added one massive outlier to the end of this set, it would pull the standard deviation significantly higher, distorting our view of the typical values. We need a robust alternative that remains stable even when the edges of a dataset are extreme. This is the role of the interquartile range, or IQR. We start by dividing the ordered data into 4 equal segments, with each representing 25% of the observations. We find the median of the full set, then identify the medians of the lower and upper halves. For this data, the lower quartile, or Q1, is 3,550. The upper quartile, Q3, is 6,150. By subtracting Q1 from Q3, we get an IQR of 2,660. This is the width of the middle half of the distribution. Because the IQR isolates the middle 50%, it is functionally blind to extreme outliers, providing a much safer measure of typical spread. To make these calculations useful for rapid analysis, we translate them into high-density visuals. This is a skeletal box plot. It is the visual summary of the data's spread and center. The whiskers extend to the minimum value of 1200 and the maximum of 7700. The box itself is defined by the lower and upper quartiles, representing the IQR. Finally, the internal vertical line marks the median at 5150. A clean box plot allows analysts to spot hidden skewness instantly. In this set, the internal median line is closer to the right edge, and the left whisker is significantly longer. This shows the data is skewed toward lower values. Some analysts prefer a modified box plot, where whiskers only extend to the nearest non-outlier, and extreme values are plotted as individual dots. This single geometric form captures the center, the spread, and the shape of an entire distribution. Why do we put so much effort into these metric models? The ultimate goal is comparative analysis. Statistics allow us to compare different groups or strategies side by side. Using a shared scale, we can compare medians, assess the overlap of IQRs, and identify which groups produce more extreme outliers. A wide box plot indicates unpredictable outcomes and high variance. A narrow box plot suggests reliability and consistency. Statistical variability provides the foundational signal of the data, capturing the very context that a simple average is designed to hide. Whether we use the mathematical precision of standard deviation or the visual geometry of a box plot, quantifying spread is the only way to truly measure reality.